state counting from the gravitational path integral. And this has, I'll describe work that has recently appeared with Joaquin Turiachi and Samir Murthy that appeared about 2 weeks ago. But throughout the talk, I'll also reference a number of past works involving these collaborators. Great. So for the past couple of years, there has been tremendous progress in understanding the extent to which the gravitational path integral for various black hole observables reproduces standard observables in conventional quantum mechanical systems. However, there are still many open questions in understanding the equality between these two sides. And in this talk, I'll try to address 3 related questions for the special case of extremal and near extremal black holes. Okay, so here are the 3 questions. Question number 1 that we would pretty much like to know of any quantum mechanical system is what's the energy gap between its ground state and its first excited state? Or in the case of extremal black holes, we would like to understand the energy gap between extremal states and the lightest near extremal states in a sector of fixed charge. So there have been numerous speculations in the past about what this energy scale is. And in the 90s, there have been a number of string theory constructions by Maldacena, Susskind, and Strominger that have supported the idea that this energy scale coincides with that at which the black hole experiences a breakdown of thermodynamics. So what happens as the temperature of an extremal black hole is lowered is that eventually the energy of the radiation of a single Hawking photon is sufficient to take the black hole from being near extremal to being purely extremal. So in other words, a single Hawking photon can change the temperature of the black hole by an order 1 amount. And therefore, people said that that's the energy scale at which there's a breakdown of thermodynamics occurring. And just for reference, since you'll encounter this scale throughout the talk, for Reinstein-Nordstrom black holes in flat space that has charge Q, this energy scale that I'll call E gap, but keep in mind that this is just speculative. It's not necessarily the true gap scale of black holes, was found to be 1 over Q cubed. The second question that I'd like to understand is whether extremal black holes are truly degenerate. Namely, the semi-classical calculation suggests that if I just look at the action of extremal black holes that are at 0 temperature, then the gravitational path integral suggests an answer that's proportional to e to the area over 4g Newton, even for such black holes. So these black holes are very low temperature, but it can have arbitrarily large area since the area scales with the charge of the black hole. However, if a partition function at 0 temperature should be truly interpreted as a degeneracy, one could wonder what actually protects this degeneracy if it's actually there. In the case, especially in the case of non-supersymmetric black holes, there's valid reasons to wonder whether the gravitational path integral description that gave you that the degeneracy was proportional to the e to the area, there's reasons to wonder whether that's valid. Now, suppose that we find that indeed such black holes have a degeneracy. If black holes are genuine quantum systems, then the degeneracy they experience at extremality should have a valid Hilbert space description, which means that this degeneracy should be an exact integer. And this has been seen in string theory examples where the degeneracy, or rather index, of various black holes has been exactly computed and was found to be an integer almost by construction. So the question that I have is, can the gravitational path integral in fact reproduce the microstate count found in string theory, including the integerness of such a count? Any questions so far about the 3 questions that I'll attempt to answer?
Yeah, I have a question. Like,
Yes.
why do you expect that the string theory answer should be equal to the gravitational answer? Because are you taking the alpha prime going to zero limit for the string theory at the end?
Yes, yes, yes. So, especially in the example that I'll be giving, the string theory answer computes an index. There's a way that I'll explain shortly for which the gravitational path integral can compute exactly the same index. Since we believe that the index should match between weak string coupling and strong string coupling, we should really see the two quantities match. So that's the philosophy here. And in fact, we'll see that more is true. We'll see that not only can the gravitational path integral produce an index, which is a protected quantity, but it can also show you that the index is equal to the degeneracy. So yeah, I hope that answers the question.
Okay.
Okay, so to start, one could perhaps think that the gravitational path integral needs to take into account quantum corrections to actually produce the correct degeneracy of all extremal black holes. So let me briefly review how the degeneracy looks like if one includes the leading order quantum corrections. So these were computed in a series, especially in a series of papers by Sen and collaborators. And the result for the degeneracy was always found to be an exponential of the area over 4G Newton. And the entropy itself was found to have corrections that were logarithmic in the area over 4G Newton. I'll just call it this quantity S naught, past which there was a series of perturbative corrections that were not really computable because they came from higher loop corrections in 1 over S naught. And there's many other types of corrections. But even if you trust that these quantum corrections are correct, if I scale S naught to be large by scaling the charge to be large, so for instance, for black holes, the Einstein-Nordstrom black holes in flat space that I mentioned earlier, this quantity S naught would go like pi q squared. So scaling Q to be large would still produce an inexplicably large degeneracy, regardless of whether I study a black hole in supergravity or a black hole in Einstein-Maxwell theory. So to answer question 1 and question 2, for both non-supersymmetric and supersymmetric extremal black holes, I want to quickly revisit the computation of the logarithmic corrections that Sen and collaborators performed. So the idea that they had was to just look at the near horizon region of the black hole and to assume that the entire contribution to the black hole entropy comes from this region, that modes that live both in the near horizon region and outside don't contribute to the entropy. The near horizon of extremal black holes, as many of you know, looks like ADS2 times S2. And for instance, for black holes in flat space, the radius of ADS2 happens to be equal to the radius of S2. Now the strategy to compute quantum corrections to the entropy of such black holes is literally to take all the fields that I have on this background, including the metric itself, and expand the small perturbations around it. After that, I can plug in these perturbations h mu nu, and let's say the perturbation a mu for a gauge field, and many other perturbations for scalar or fermion fields that live in my theory. I take all these perturbations, expand my action to quadratic order around this background, and compute the one loop determinant of every field. So it's fairly intricate, but this has been known to, the way in which people have done this was using the heap kernel on the ADS2 times S2 background, which turns out to be fairly simple. So there are two types of modes for all these fields that we can discuss. First, there are modes that have non-zero mass or non-zero eigenvalue under the differential operators that appear in the quadratic expansion of the action. And for those, the heap kernel can be computed unambiguously. So the one loop determinant for those modes gives us S naught to some power C non-zero, where C non-zero depends on the number of various massless fields. And I'll show you in a couple of slides more concretely what it is. However, in addition to these, there are zero modes of the action. And these zero modes are of two types. They're either large diffeomorphisms of the metric or large gauge transformations. So both large diffeomorphisms and large gauge transformations physically change the space-time that I'm studying or the field configuration that I'm studying. So for instance, large diffeomorphism can change the location of the boundary, can change the shape of the boundary. They don't change the proper length of the boundary, but they could, for instance, affect the extrinsic curvature of the boundary. So they have an observational consequence, and I should not quotient them out from my gravitational path integral. And the same is true for gauge transformations. So one in principle, yes.
If you included, you have this ADS2 and then it's connecting to flat space eventually. And if you included the flat space part, then this mode that you're calling a large diffeomorphism would be a non-diffeomorphism. Is this right? It would genuinely change the space-time once you include the patching.
Yes, it would change the way in which the near horizon region is glued to the asymptotic space-time.
And so the action of the full, there's no sense in which it is gauge equivalent to the original background.
Yeah. There's no sense. Yeah, even if you include the full geometry, the geometry still looks different when you act with this sorts of perturbations that have zero eigenvalue in the near horizon region.
Yeah, so then it's absolutely clear it's physical and you have to include it.
Yes. Great. So these zero modes are present at zero temperature. And as I said, what they do, the perturbation of the metric, is that they change, for instance, the way in which the near horizon region is glued to the rest of the space-time, the asymptotically flat space-time that exists past that. What Sen and collaborators did very elegantly was to extract from the path integral over the zero modes. The zero modes don't have any weight, but they could still carry some non-trivial dependence under S naught through their measure. So if one considers an ultra-local measure in the gravitational path integral, you could actually explicitly extract what the dependence of h mu nu is on S naught, because S naught is the overall scaling of the space-time. So that appears in the ultra-local measure. And in total, if I take into account the contribution that I get from the heat kernel and the contribution that comes from this measure of the zero modes, then one gets a power of S naught that's given by the number of massless scalars, massless vectors, and massless fermions. This number comes from the gravitational mode itself, comes from fluctuations of the metric. But one thing remains. What remains is an integral over the integral over the zero modes, but now that integral was completely stripped of its S naught dependence. So the remaining integral that one has to do in order to actually compute the one loop determinant now is S naught independent, and in principle gives a constant. However, if I naively look at the volume of this space, the volume of large diffeomorphism quotiented out by isometries, this volume is formally divergent, and I have to understand how to regulate it. And there's three options. It either gets regularized to zero, it either gets regularized to a finite value, or who knows, it might even be regulated, it might not be regularizable. And in order to actually answer what the partition function of such black holes is, I have to decide or have to understand what the regularization of this path integral is. Yes.
So here you're assuming that the the S2 doesn't have any deformations. I mean, it could
Oh,
also...
no. I just didn't write them down. There's actually zero modes associated to S2 as well. So when I wrote the perturbations of the metric, I wrote them formally. I didn't want to bore you with all the directions in which perturbations are considered. But here we consider both perturbations in the ADS2 direction, in the S2 directions, and mixed perturbations. And in fact, there are zero modes associated to large diffeomorphisms that not only change the location of the boundary, but there's also large diffeomorphisms that affect the relative rotation of S2 as one goes around this boundary. And these will actually turn out to be very important, especially for supersymmetric black holes. And when I wrote this down, it was more formal formally to like visualize what some of these large diffeomorphisms do. Technically, this large diffeomorphism for the case of black holes in Einstein-Maxwell theory live in the space diff S1 times loop of SU2. So diff S1 just come from fluctuations of the boundary of ADS2, as I picture them here, but loop of SU2 come from the fact that as I go around the thermal circle, as I go around the boundary of ADS2, I can have fluctuations that rotates the S2 at the same time. And those fluctuations in the rotation of S2 can be conveniently described through an SU2 group element. And so you can think about these large diffeomorphisms, the specific large diffeomorphism, as being an SU2 group element that's valued at every point on the boundary of ADS2. So that's why it's loop S2. And this has to be quotient out by the isometry in the near horizon region, which is SL2R, which acts on diff S1 times SU2. So that's how the S2 is included.
Oh, sorry, Shiraz, just very quickly, Luca. So for if you had a U1 symmetry in general, say in a near extremal Reisner Nordstrom, then we know that besides diff S1 degrees of freedom, you also get phase rotations with a action similar to the Schwarzian. And this loop SU2 with its suitable quotient seems the SU2 generalization of that. Would I be right in thinking of it like that? Or
that's right. That's right. That's precisely right. In the case of a gauge group, you just have loop G over G.
Yeah.
Quotient parametrizing the large gauge transformations of that gauge group. And you could think about these rotations of S2 as large SU2 gauge transformations associated to the SU2 gauge field that appears in the dimensional reduction to the near horizon region of the black hole.
Yes, thank you very much.
In fact, though, what's very important is while in the case of I'm getting a bit ahead of myself, but while in the case of Reisner-Nordstrom black holes in flat space, this is the group of large diffeomorphisms. In the case of supergravity for supersymmetric black holes, the two mix into a single bigger group. The diff S1 and loop SU2 mix into a single bigger group that has fermionic degrees of freedom associated to super diffeomorphisms. Yes, I think there's another question.
Yeah. Hi, Luca. Hi. You just said that this loop SU2 is coming after dimensional reduction to the extremal near horizon geometry. Did I understand you correct?
Yeah, that was just Yeah, that was just a concrete example of why it's actually identical to this case of gauge fields. But you don't necessarily need to think about an actual dimensional reduction. You can just do this this kind of deformation of the space-time and see where the fluctuations of the metric live in, the space in which the fluctuations of the metric live in.
Okay, so you didn't really reduce it over S2.
No. This is just taking the 4D geometry and actually perturbing it. In fact, here in this talk, and at least in the first part, I want to follow as much as possible the same approach that Sen and collaborators had.
Thanks.
Sorry, Luca. If I think of this black hole as embedded inside 4 dimensions, then you told us how the first part, this S1 could be thought of as sort of changing the embedding inside 4 dimensions. But now the S2 is also part of the embedding in 4 dimensions. So is this whole thing just sort of the shape of the membrane in 4 dimensions? Or?
I think this part loop SU2 can be thought of as literal rotations, possible fluctuations in the rotation of the black hole. So as you go around the time circle.
So if I specify sort of an embedding of the horizon inside R4, would that carry the same data as your diff S1 and loop SU2? Is it just like
yes,
in R4?
Yes, I believe so. Yes.
Yeah, thank you.
Yes. Okay, maybe let me move on. Yeah, so we want to understand how to regularize this remaining integral that's independent of S0.
One more quick one. So your integral is now on an ADS2 times S2 of unit size. Is this right?
Exactly. Yes. So I rescaled the space to get completely rid of all units that are related to the charge of the black hole. Good. So I want to understand how to regularize this integral. And in order to regularize any partition function, it's actually good to compare it to a partition function where a different parameter is turned on, assuming that partition function also gives a finite result. And in this case, we will regulate the path integral over 0 modes by going to finite temperature. So we will no longer expand our metric around the purely extremal background. Instead, we will take our extremal background, turn on temperature, which changes the background classically just a tiny bit. It takes the black hole from extremality to near extremality and changes the near horizon geometry, because now the radius of the S2 starts varying as I move away from the horizon. And consider the same fluctuations of all the fields, but now in this new background. What happens, and that's very nice, is that the change of classical background now gives a non-zero weight to all the 0 modes that were present at t equals 0. So because of this, these 0 modes are not actually there at finite temperature, so I'll just call them would-be 0 modes. Now, for Reinstein-Nordstrom black holes, I can see what the action of these 0 modes are. Since now they have a non-zero mass, I can actually see order by order what term I get in the expansion. So if I parametrize the space of these 0 modes, the 0 modes that end up being important are just the ones in the fluctuation of the ADS2 boundary, or rather in the gluing of the ADS2 boundary to the asymptotically flat space. So there are these modes that live in dFS1 over SL2R. If I look at black holes in the canonical ensemble. The answer for the gravitational path integral is now given has 2 parts. The first part is the old that included the classical entropy. The classical entropy and its quantum correction. But now this integral over this would-be 0 modes is an integral over a mode parametrized in dFS1 over SL2R. And the action that one finds on the nose by literally expanding this four-dimensional action in epsilon mu is the so-called Schwarzian action, which is a higher derivative action whose coupling is coincidentally given by the scale E gap, 1 over E gap, that I mentioned at the beginning of the talk. So the coupling of these modes is now connected to the energy scale at which the breakdown of thermodynamics occurs. So this was the scale 1 over E gap that we saw at the beginning of the talk.
Question.
Yes.
So this order 1 over S0 correction would, I suppose, come from the SU2 part, loop SU2 part, right?
Oh, sorry, this part?
Yeah, I mean, I'm just concerned about what happens to the S2 part that you just talked about earlier.
Yes. So there's a similar, effective theory. I can write it down. What effective theory you get when you expand these fluctuations for the rotational bit. And what you get for the rotational bit is you get a particle living on the SU2 group manifold as your action. And the coupling of that action also happens to be related to the scale. Now, the difference between why I didn't write that action is because if you go into a sector of fixed angular momentum, that's like fixing a representation in the Hilbert space of that particle moving on an SU2 group manifold. So the particle moving on an SU2 group manifold can be quantized, and its Hilbert space can be classified according to representations of SU2, and the ground state is a singlet that carries 0 spin and has degeneracy 1. So if I look in a sector of fixed angular momentum that has J equals 0, so here I'm looking at a black hole that has fixed Q and fixed J, the only remaining integral that I have to do is over diff S1 over SL2R. And the difference between this theory of zero modes, I call them maybe zero modes, and the other maybe zero modes is that the other zero modes have a spectrum that's gapped. This theory turns out to have a spectrum that's continuous. So it will affect in the energy density, the density of states of the black hole in a much more drastic way. I can come back to it when I'll show you a plot of how the density of states of this black hole looks like. Yes.
So Luca, does that mean that to get to this action, you have actually considered a black hole which has J equal to 0, and hence effectively, I mean, you explained it as the representation on that group manifold, but effectively you can just forget about the S2 part.
Yes, that's right. Yes, but it's actually quite, we'll see in the supersymmetric case that it's actually quite subtle how to fix J equals 0 or how to fix the angular momentum of the black hole. So I'll come back to that in a little bit of time.
And so, sorry, just to make sure I'm understanding,
yes,
the difference for the S2 part is that the group manifold there is compact. That's why there's a gap.
Precisely. Loop SU2. The isometry group is compact. And the field space is compact. That's the difference.
Right.
Yeah.
Right. Okay. Thank you.
Another thing that while regularizing on top of taking finite temperature, shouldn't you also be taking finite J and then going to the J equal to 0 limit as you're doing for the temperature?
Again, in principle, I could write down the exact path integral for all these zero modes because I can take my 4D action and expand it to quadratic order. And in particular, for these zero modes, there is a trick to determine the contribution at even higher order than quadratic order. For zero modes, in principle, you want to know the action exactly when they're lifted because they might stay strongly coupled. You can do that for the rotational mode as well, and for all other large gauge transformations, and you could do the integral exactly. So I can write down the black hole partition function as a function of T, Q, J, and whatever else you want. And then I can take the ratios between these partition functions and see what, how these integrals get regularized. In principle, the only one that's divergent is this integral over dFS1 over SL2R. The others over loop SU2 over SU2 turn out to be finite and kind of less ambiguous. So the important thing here is that this theory, it turns out you can rescale time in this Lagrangian to, yes.
Look, I'm really sorry to interrupt you, but could I ask?
No worries.
That is probably a stupid question, but
yes.
As we discussed earlier on, once you include the gluing of the space to flat space, this mode that looks like a diffeomorphism is no longer a diffeomorphism. And I would have imagined that would be true even in the exactly extremal situation. So I was wondering whether including the gluing to flat space and making sure that the vibrations happen in a region where that gluing is not negligible would be another way of regulating this problem, or is that completely different?
I don't think so, because yeah, I think you can include these fluctuations exactly on the extremal background, and as far as I know, they remain zero. They still are zero modes.
I see. So there is so you say there is a diffeomorphism. That is a diffeomorphism of the full geometry, including going off to infinity, and that is not localized. Of course, the one way that could happen is that it's just localized very far down the throat, so that the fact that you've glued on doesn't matter. But if you move your diffeomorphism to a place where the gluing starts being visible, there is still an exact diffeomorphism. Is that what you're saying?
You mean in the extremal case?
Yes, in the extremal case.
Yeah, yes, I believe so. I believe it still remains a large, in the extremal case, I think still remains a large diffeomorphism on the entire. Well, I'm not sure if it's a large diffeomorphism. What I know for sure is that it's a zero mode, which is which can be a different statement.
At least, I'm sorry to interrupt, but Luca, at least when we with Upamanyu and others, when we did these calculations, we did look at the exact extremal limit, and at least what we found there was that it wasn't an exact diffeomorphism all the way out to infinity, which is why you got a cost in action, but it was a zero mode, That's what I would say, but okay.
So does that mean that at the nonlinear level, it wouldn't, it would pick up action?
Yeah, this Schwarzian is the action you pick up,
What do you mean at a nonlinear level?
But what I was thinking was that when we say it's a zero mode, it's some statement about quadratic fluctuations.
Yeah. No. That's not the case. In the case of extremal black holes, you could actually check that this is an exact zero mode. It's not that you can go to higher and higher orders, and to all orders you'll find that it's zero. And this is what this action shows, in fact, because if I scale the temperature to zero, you get let me just go through this. So in this integral, I can rescale time such that the integral, so I can define u tilde to be 2 pi over beta times u, and one completely gets rid of time here, and under this diffeomorphism, it turns out that the Schwarzian, together with the measure of the integral, transforms in such a way that the overall scale of the temperature moves as a constant prefactor in front of the integral. So the actual coupling of these modes, this is not only quadratic, this is to all orders in epsilon. The actual couplings of this modes is given by T, the temperature, over E gap. So in the limit when T goes to 0, you could actually see that these modes completely decouple to all orders.
I see. And if I understood right, you're doing this calculation within ADS2. I was wondering whether that same statement held also when you include the patching onto flat space. You said
you mean the statement about the higher order terms?
Yes.
Yeah, I think at extremality it does, but I'll double check and let you know if that's not the case.
Okay, thank you.
At extremality, well, there are corrections to this that scale as in powers of epsilon, where epsilon is the cutoff of the size of the ADS2 times higher powers of the Schwarzian action. But those at extremality still go to zero, because the scale epsilon at which you cut off your ADS2 times S2 space-time also goes to zero. So I believe that even that all higher order terms, not only the quadratic terms, vanish when you include the gluing.
So one last thing, and I'll stop being reserved. It sounds like what you're saying is that because you're doing these diffeomorphisms so far down the throat that you don't see them at the patching region, of course, then the patching doesn't matter.
Right.
Okay.
Yes. And technically, the extremal black holes have an infinite throat. So
yes,
the proper distance of these.
Yeah.
But you could do a diffeomorphism. You could take the limit where the temperature goes to zero, but keeping where you're doing your diffeomorphism sort of fixed in relation to where the patching happens. Now, in that situation, it would affect, right? It would not be a zero mode anymore. I'm asking because, my mental picture was that there was the shape of the membrane, which is wiggling. And it sounds like you're saying that the thing that's in exact zero mode does not affect the shape of the membrane, because it happens so far down the throat that it doesn't affect the patching region at all.
It does not affect the shape of the membrane. You mean that does not affect the extrinsic curvature? Oh, I can't hear you anymore.
It does not affect the way the membrane is embedded in our form.
Well, I think it does in a physical way. Otherwise, we should in principle quotient by this mode, right? Otherwise, we're counting geometries that are identical, right?
This is why I'm asking. If you push your diffeomorphism so far down the throat that the effect of the diffeomorphism doesn't survive in the patching region, then it seemed to me that was the statement that it did not affect the embedding.
No. Well, I don't exactly understand what you mean by pushing it down the throat, since these are large diffeomorphisms. They affect the ADS2 boundary by a large amount. So they affect precisely this region in which you glue the ADS2 to infinity. The diffeomorphisms that I think are deep down the throat are the small diffeomorphisms that don't affect the gluing region at all.
Yes.
Okay.
Yes.
Okay. So you said that there is really a way of changing the shape of the membrane in the extremal case that is exactly zero energy.
Yes, I believe so. Yes.
Okay, that's very
okay.
interesting.
Luca, you must
Yes.
go on, but just to say, at least what we got was something different, and just to say, if Shiraz and Luca, the asymptotics in flat space are more complicated than in ADS. So take a ADS4 to ADS2. Flow. Then what we got was, you're absolutely right, these modes corresponded to large diffeos in the ADS2 region, but they continued to cost in terms of action even at the extremal limit. And the relevant scale there is the chemical potential, if you're talking about energies as of the black hole as measured in ADS4. That's an energy scale. And that was the relevant scale. But okay, this is what we got. We can discuss how it connects to the finite temperature and all, if you like. But anyway, please go on. Maybe later on, I can try to dig up. Okay.
Thanks, Andy.
One last point. When you take the temperature to zero, finally, this entire expression will go to zero for the non-supersymmetric case, right? So
even for the supersymmetric case, it goes to zero. Yes, in both cases, it will go to zero. There's zero modes in both cases.
No, I mean the diff S1, the integral over the epsilon, that goes to zero even for this supersymmetric case.
No. Sorry, I thought you meant that the integrand, the exponent, goes to zero.
No,
you mean the whole integral goes to zero?
Yeah, the
Yes. That turns out to be the. I'll get there. Yes.
integral goes to 1 for the non-supersymmetric case, I guess, right?
For the non-supersymmetric or for the supersymmetric?
That is
For the non-supersymmetric, this integral goes to 0.
goes to 0. Okay.
Yes,
Now,
I'll show that in a second.
Yeah.
Yeah. So,
in
the point that
in that case, shouldn't you be also considering the fact that you can kind of deform the, I mean, you should take T, not only TQ, but TJQ, because finite J going to 0 would give you something finite instead of just 0. And that would alter things, right?
No, even if you fix the angular momentum to a different value, you'll still find that the density of states in that angular momentum sector will go to 0 at extremality. Maybe maybe I'll just continue for a bit, and I'll just show you the punchline for non-supersymmetric versus supersymmetric, and then you could ask me how, if you still have a question. So yeah, the important thing is that the coupling of this theory, the effective coupling that this theory have, can be viewed as T over E gap. So if we want to study these black holes in a regime that's really close to extremality, what's happening is that these zero modes, these would-be zero modes that were described by epsilon, become very strongly coupled since T over E gap becomes very small. The classical regime is the one in which T over E gap is very large, in which case you can actually solve in which case this path integral localizes to a saddle point of this action, and the saddle point is known. So if I want to really understand the black hole at very low temperatures, I have to understand this strongly coupled theory of the would-be zero modes, and this actually signals the failure of semi-classical physics that was previously noticed in the 90s by Preskill and collaborators. However, this makes things very precise because it turns out that this path integral is exactly solvable using fermionic localization. And this is something that was done by Stanford and Witten. So in total, if I perform this path integral and put it together with the old results for the corrections to the quantum corrections to the black hole entropy, one finds the following. In addition to the quantum corrections to the entropy that appeared as log S0, there is a classical correction that appears at low temperatures that scales as e to the temperature times 1 over this E gap scale. And in addition to that, there is very importantly a one-loop determinant piece that is temperature dependent. So the classical piece is actually not that important in the limit of 0 temperature, because as the temperature is decreased, this goes to 0. So e to the 0 is just 1. However, at low temperatures, this one loop piece becomes dominant. And in addition to that, the fact that the one loop piece actually depends on the charge of the black hole means that if I actually want to determine the logarithmic corrections in the charge of the black hole to write what the log Q term of the partition function is, this term has to be considered as well. So what one finds is that the ratio between the black hole partition function at t equals 0 and the black hole partition function once the temperature is slightly raised goes to 0 as this temperature goes to 0. And one can actually make this more precise by tracking down what sort of interactions we neglected for these would-be 0 modes. And it turns out that you have sufficient control over all perturbative interactions in the would-be 0 modes. The only things that we start losing control over as the temperature becomes small are non-perturbative terms. So in principle, the degeneracy of extremal non-supersymmetric black holes from this is exponentially suppressed compared to the expected results. So instead of going like e to the S0, where this is 1, it has to go like e to some number times S0, where this number is smaller than 1. And in principle, if you trust, more recent, quantum mechanical models for these extremal black holes, like what people discuss in SYK, whose spectrum is also related to the Schwarzian theory, one in principle could believe that these black holes are completely non-degenerate, since in these models the spectrum is completely non-degenerate, as one would expect by symmetry arguments. However, the best way that we can do at this point with the gravitational path integral is to say that at most the degeneracy is given by non-perturbative correction.
Luca, sorry, one question.
Yes.
So going back to the massive modes, when you integrated them out, you got this simple factor, which is part of the integral, right?
Yes.
Depending on the number of things, scalar vector and the fermions, right?
Yes.
So, but I would imagine that if you integrate them out in some given background of zero modes, the one loop determinant you would get from those would depend on the background, namely the
on the background of zero modes
and the such.
No, that turns out not to be the case. It turns out that there's a sort of decoupling that happens even at quadratic order between the zero modes and the non-zero modes.
I see. So can you say like how does that happen? Because I guess generically you wouldn't expect that. Perhaps is it what nature of the zero mode makes it possible?
I think it's just because it's a large diffeomorphism, and the way in which this action at finite temperature appears, the way in which the weight of the zero mode appears is through a boundary term at the edge of the ADS2 region. It's through the Gibbons-Hawking-York term. And in there, you don't actually couple to the other non-zero modes explicitly.
Okay, got it. Thank you.
So one can take this partition function that's exact up to 1 over S0 corrections.
Sorry, Luca.
Sorry, that's good. And then up to leading order in a 1 over S0 approximation. Sorry, go ahead.
Just one continuation of that. But the SU2 background, it also have the same property that it's given by the boundary term?
Yes, I believe so. Yes.
Okay.
Well, we explicitly expanded this action, and well, you can either do it, as I said, for this dimensional reduction, but for this paper that was more recent, we actually did it fully in 4D and actually expanded the action to quadratic order to see the couplings between the non-zero modes and zero modes, and they decouple. And
okay.
Another question, like in the temperature going to zero limit, are you saying that the entire partition function goes to 0 because of the t to the 3 by 2 term?
Yes. In a 1 over S0 approximation. This is the leading thing in e to the S0.
Okay, so this is a leading thing. It's not the exact answer.
This partition function can receive non-perturbative corrections in e to the S0 that we don't have control over. The best that we can say is that this is the answer. So this answer is correct in the sense that it has 1 over S0 corrections. We can check that all the 1 over S0 correct. If we gave an argument that all the 1 over S0 corrections come with positive powers of the temperature, which means that the only corrections that can survive in the limit t goes to 0 come from non-perturbative corrections. And unfortunately, those we don't have control over because who knows, maybe there's a very non-symmetric solution that has an action that's slightly larger, and that contributes, who knows, maybe that that one doesn't have a one loop determinant that goes to 0 at extremality. So that we don't have control over.
I'm just concerned about the fact that since Z, the partition function is proportional to e to the S0. If that thing goes to 0, then what happens to the entropy?
Right. So in principle, the entropy should not be minus infinity, right?
Yeah.
The entropy should be bounded by 0.
Yeah.
But that can be easily achieved by non-perturbative corrections. For instance, if there's some geometry that miraculously contributes 1 to this partition function, or some number of order 1, which is a non-perturbative correction compared to e to the S0, the leading correction, that contribution will dominate in the regime of very small temperatures, and you will get that the entropy is the log of whatever order 1 correction you added.
Okay.
Okay, so we can take this partition function, do a Laplace transform.
Yeah. Just 1 sec, sorry. So can you just tell once more what non-perturbative correction we are really talking about? So we were
sorry, what? Okay, can you repeat the question?
What non-perturbative corrections you are really talking about here? I missed that point. Because I thought we are considering all possible fluctuations and taking their contributions, no? And our background is whatever, like
perturbative fluctuations. You can, for instance, take a classical geometry that looks completely different, right? One example that we know of are fragmented black holes. So there's black holes that satisfy the same asymptote, that are asymptotically flat, that are multi-centered, as an example. And those, I don't know yet if their contribution to the partition function also goes to 0 in the limit t goes to 0. But those also have the property that their action is just different, right? Their classical action is different and is suppressed compared to the action of the Reinster-Nordström black holes. So those are non-perturbative contributions to the partition function. And that we don't have control over, because that's like going far, turning on some of these modes, not only the 0 modes, but also some of these other massive modes. You can, turn them on very large, deform the metric so much that you reach another saddle. That's always a possibility, and that we cannot constrain.
And continuing along similar lines, I mean, if you have corrections that are order of 1 by S0, how would you get, when you take the log, you wouldn't get S0, right? I mean, when you take the log of the partition function, so the first term wouldn't be S0 in that case.
No, so the corrections that I was talking about were not the log of this 1 over S0 piece. It was if, in addition to this, you have corrections that go like even like non-perturbative corrections that are not multiplied by this factor of t to the 3/2. So all these loops, you can give an argument that this thing is a regular function as t goes to 0. We can't actually compute them exactly, but we can actually write down the interactions between the 0 modes and non-zero modes to various orders, and see whether or not from those interactions we can rescale the modes with t to see whether this piece is regular or might be divergent as t goes to 0, and we found that it's regular. Now, the thing that I was talking about, which means that this entire thing that I wrote down really goes to 0 as t goes to 0. What we really don't have control over are further corrections, which are of order e to the minus S0 in this parenthesis. So in total, they contribute e to some number times S0, where this number is smaller than 1. And these might correspond to other classical solutions that satisfy the exact same boundary conditions.
But if that number is negative, then don't you have a problem?
This number?
Yeah, you say order of e to the minus s naught.
Well, it's order e to the minus s naught compared to the leading answer. I said that order e to the minus s naught is in this parenthesis. Sorry, I didn't. Yeah, in this parenthesis, which means that overall, the answer is e to some number times s naught, where that number is smaller than 1.
Okay.
Anyway, let me not, dwell further on this point. So the density of states, at least if you take the perturbations around the leading saddle, indeed seems to go to 0 as the energy goes to 0. And at large energies, here I compared it to the answer that one finds by just Laplace transforming the density of states, which without taking into account the quantum corrections from the Schwarzian theory. So without taking into account this temperature-dependent one-loop determinant. And we see that at high energies away from extremality, the curve that takes into account the quantum corrections and the curve that doesn't are very close to each other. However, as I go towards extremality, in particular, when I passed the scale, that was the scale at which a breakdown of thermodynamics was discovered, what one finds is a greater and greater the difference between the classical density of states and the quantum corrected density of states, until eventually at extremality, the density of states goes to 0, as I already mentioned. So to answer question 1 and question 2, in the absence of supersymmetry for an Einstein Maxwell theory, one finds that the theory has no gap. The spectrum is very dense. It's non-perturbatively dense, it turns out, and has no exact degeneracy at extremality at the order e to the s naught. How about black holes that preserve supersymmetry at extremality? If we find a similar result in that case, then we're in big trouble. Yes.
Just a moment. I mean, so you get the rho of E by Laplace transforming the Z, right?
Mm-hmm.
So the Z in the temperature going to 0 limit is just 0.
Mm-hmm.
So when you Laplace transform that, what do you expect?
Rho to go to 0, right? As he goes towards extremality.
Yeah, but then that means that the entire rho of E should be 0. I mean, why should it have a profile?
Oh, what do you mean?
He's accounting for the approach to 0. It's not just Laplace transforming 0.
No. So in the temperature going to 0 limit, which you are considering, which you are concerned about, the Z goes to 0. Now the Laplace transform that would also go to 0, right?
Yeah, you can't take the Laplace transform of a function only at a single point at which that function is defined. We're just talking about, we can take a polynomial, right? So let me just give you an example. So if I take the Laplace transform of rho of E, where rho of E goes like e to any power, e to any polynomial power, and take e to the minus beta E times dE. If this power is positive, such that rho of E goes to 0 as E goes to 0, then it turns out that this function goes to 0 as T goes to 0. Does that answer your question?
That is okay. But if you start out with a Z which is also 0, and you take the Laplace transform.
It's not 0. It's some function of T, right? It's function of T. You saw the explicit function of T.
No, in the limit. Okay, so it's
why are you taking the limit? The Laplace transform requires all of it.
Yeah, correct.
Yes. Okay. Thank you.
All right. Good. So what about black holes that preserve supersymmetry at extremality? If we would get the same density of states there, we'd have a really big problem. For instance, we know from the counting of Strominger and Waffe that the index of such black holes is very large, which guarantees that the degeneracy of such black holes is also very large, which means that we should find a very non-trivial spectrum as the density of states goes towards extremality. Sorry, as we look at the density of states at extremality. So for supersymmetric black holes, and it turns out that in both ADS or flat space, the same one loop computation and accounting for the would-be zero modes leads to a wildly different conclusion. And for the non-zero modes, the calculation proceeds in entirely the same fashion. People have gone and computed the heat kernels for all the modes in supergravity on these backgrounds. And the only missing ingredient was, what's this integral? Now, instead of doing it over the space of diffeomorphisms, we have to do it over the space of large super diffeomorphisms, quotiented out by the space of superisometries. So for the black holes that were discussed by Strominger and Waffa, or the black holes in flat space and 4D supergravity that I'll describe in a bit in my talk, the space of large diffeomorphisms turns out to be a superspace that's diff S1/4. So it's a generalization of diff S1 times loop SU2. Diff S1 times loop SU2 is the maximal bosonic space that can be embedded in this space. And the superisometries in this case are PSU1, 1/2. And the wildly different result is that if I now integrate over these large super diffeomorphisms, these not only fluctuate the boundary, the location of the boundary, they also fluctuate the position of the circle and the value of the gravitational at the boundary of ADS2. What you get, instead of getting 0 in the 0 temperature limit, you find that the answer is 1 when you regularize it. And you could actually compute this more explicitly by going to finite temperature, once again finding this effective theory of the would-be zero modes, finding the temperature dependence of the partition function, take a Laplace transform of that, you get what the partition function of these black holes is. And here it is. This is the density of states of such black holes, where we now see that at extremality, there's a huge degeneracy of states that's actually given by e to the S0 times S0 to some non-trivial power that depends on the number of free massless fields in the supergravity theories. So all these modes here, what I'm showing is rho of E for modes with all angular momenta. And here you could actually see, it's not shown on the plot, but you can actually show by computation that the only modes that contribute at extremality here all have j equals 0. They have a exact 0 angular momentum. And you might wonder why you see this weirdness in the density of states as the energy is increased, why you see these discontinuities. That's because the density of states for different supermultiplets of in this effective theories has different gaps. And what you see going between here, what you see here is a gap. The first gap, past which we see a supermultiplet that has j equals 0 and half. And past that, you see another supermultiplet appearing that has j equals 0, half, and 1, from what I remember. And you could go and plot the density of states for every value of j that you want. But the important feature now that answers question 1 and question 2 that I posed at the beginning is that for black holes in supergravity in flat space, there is a gap and a massive degeneracy consistent with the expectation from microstate counting. And actually, it's also consistent with the string theory constructions of the gap. In particular, Maldacena and Susskind predicted an exact scale for the gap, and that scale is found to agree with this one. It was more of a guess, since the computation that they do was a computation done at weak string coupling that tried to extrapolate to strong string coupling. So it wasn't really trustworthy, but it was almost guaranteed by dimensional analysis that they would get the right answer. You had a question?
Yeah, Luca, sorry. The question is, what sort of features in the temperature, the partition as a function of temperature gives rise to this gap? Because an
Yes,
interesting way
yes.
to understand that.
Yes. Sorry, I didn't mention it, so I'm sorry about that. The feature that that gives you that is the following. Once again, you can write the gravitational path integral as in terms of this integral over the would-be zero modes. The difference now is that this integral over the would-be zero modes contains both the dFS1 part and the loop SU2 part that are now coupled for fermionic degrees of freedom. The dFS1 part turns out to have a single non-trivial saddle. This is the saddle of the Schwarzian theory, for which this epsilon of u goes like tangent of pi u over beta. So this one has a single trivial saddle. However, the loop SU2 field in def S1/4 turns out to have an infinite number of non-trivial saddles. And those infinite number of non-trivial saddles correspond to shifts of the, so for def S1, for loop SU2, you have to fix the boundary condition for the SU2 field as you go around the thermal circle. That boundary condition, in principle, is invariant under sending your chemical potential, the value of your chemical potential, the chemical potential for that SU2 field, in this case, just corresponds to the angular velocity of the black hole. Your boundary conditions are invariant under sending your angular velocity to itself. So omega, the partition function, should be invariant under sending omega to omega plus 4 pi I over beta. So it should be invariant under these shifts of the chemical potentials that turn out to leave the holonomy of the SU2 gauge field that correspond to the black hole rotations as one goes around the time circle invariant. So these transformations leave the SU2 holonomy invariant. And for each one of these saddles, for each one of these shifts, it turns out that you find a new saddle. So in total, there's actually an infinite number of saddle points for these modes. And then you have to do the one loop determinant around each of them. And then when you Laplace transform an infinite sum, even though it's an infinite sum where each function is smooth, the Laplace transform of an infinite sum could be non-smooth. And that's what you find for the density of states. You find that while each saddle has a one loop determinant, that the one loop determinant times e to the on-shell action is a smooth function, when you sum up the density of states associated to all the saddles, you end up with an exact delta function at the origin and an exact gap. And this occurs in in a lot of quantum mechanical systems, actually. The weirdness here is that you have an exact delta function followed by a gap, followed by a continuum. But for instance, if you take a particle on a group manifold and take that system also has an infinite number of saddles. If you take the answer only from the leading saddle, you'll get a density of states that's continuous. If you sum up the saddles, you will find that the density of states becomes discrete and is a sum of delta functions.
I see. That's interesting. Thank you.
Sorry, Luca, just a quick follow-up. Perhaps this has been discussed, but you've been very careful to present your answer just in terms of path integrals. Okay, but if you're doing a path integral over some the important part's coming up from the path integral over some low energy effective action. Now we could try to go to the Hamiltonian picture for that low energy effective action and try to compute the spectrum of that quantum mechanics or that system. And
yes.
would we see this? Is the spectrum you're showing us here related to the spectrum of that quantum system?
Yes, it is. And in fact, like this was the approach taken very recently by Maldacena and collaborators. In a recent paper, they compute the quantization of this quantum mechanical system in a slightly different way than we did. So we did it using fermionic localization, because it turns out that these spaces in which you do the path integrals are symplectic manifolds. So you can use Duisterman-Heckman theorem to actually evaluate the path integrals. He did it by rewriting the ADS2 by trying to quantize the quantum mechanical theory that describes the Lorentzian evolution of the thermal field double of ADS2. So he did it by instead of taking a Euclidean circle, as we did, he cut the Euclidean circle, and you could rewrite the action of the Schwarzian as an effective action governing the length of this Einstein-Rosen bridge, this ADS2 Einstein-Rosen bridge in the two-sided black hole. So instead of having the Schwarzian degree of freedom, you have a degree of freedom that's labeled by roughly the length. And you could write down what the effective potential of this action is. And in the non-supersymmetric case, the effective potential of the action is found to not have any global minima. And in the supersymmetric case, after integrating out the fermionic degrees of freedom, in this quantum mechanical system, he found that this system has the effective potential for this length has a global minimum. And that global minimum has exactly one bounded state. So in other words, this delta function that is found here is the bounded state in the effective theory of this length. And in fact, this means not only that there's a large degeneracy, but contrary to popular belief, the geometry that describes this large degeneracy of states doesn't have an infinitely long throat, as you might naively expect classically for extremal black holes. It actually has a finite throat, a finite length throat that's given by where that effective potential achieves its minimum. All other states that you see here in the continuum were found to be scattering states in that potential. So there's a potential that looks like this.
Thank you so much. And one very quick follow-up question.
Yes.
But can I say one small thing about that? No,
yes,
Luca,
yes.
Such a good summary of Maldasena's paper also. But I find it completely mysterious because it's not what Shiraz is saying. You know, the Schwarzian actually makes no appearance in that quantum theory. It's only the length and the relative time shift as the conjugate variable. So it's a very mysterious thing. The path integral involves the Schwarzian, but it's not as if you take that dynamical system and quantize it. You know, it's
I think the two approaches are related, because it turns out that if you write their quantum mechanical theory in terms of momenta and positions, there's a way of integrating out the two momenta. So the phase space of the quantum mechanical theory turns out to be 4-dimensional. So it has 2 positions and 2 momenta. It turns out that there's a way of integrating out one of the positions and 2 of the momenta in such a way that the path integral in that theory becomes the same as that of the Schwarzian. So it's just, as far as I understand, it's kind of a non-trivial rewriting of the Schwarzian. This was initially covered in a paper by Verlinde and collaborators that realized that the Schwarzian theory is linked to what people now call Liouville quantum mechanics.
Yeah. But it
Wait,
okay. It has to be shown with the measure and so on. Anyway,
yes,
I
yes,
what
yes,
you're
yes, yes. I
saying
agree
is
that
true
it's
for the action. It because the
mhm.
measure, as you have emphasized, is all important, and I don't think it's quite been done like that. Okay, maybe
Yeah,
I
yeah,
don't know.
yeah. It has not. It has not. Well, also, yeah, it has not. Yeah.
Okay. Anyway,
Let
I'm
me.
sorry. I'm sorry. Please go ahead.
Oh, no, 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 no worries, no worries, no worries at all. I hope that answers your question, Shiraz.
No, it's a wonderful answer. Just one quick follow-up.
Mm-hmm.
In this picture that you show with this sort of scattering potential, the potential goes off to infinity. So then I
Yes.
would have expected that the coefficient behind your density of states, if I was counting states, would be infinity. Why is that wrong? Because the volume of space in this quantum mechanical model looks infinite to me.
Yeah, I think this quantum mechanical model doesn't take into account this quotient by SL2R properly. So I think there's secretly a volume of SL2R that people divide out to get to the exact density of states. It's a bit sketchy how it's done. So I don't entirely, as Sandeep said, it's related to the exact measure for the path integral of this quantum mechanical model. For in the Schwarzian, we quotient out SL2R because that's an actual isometry of the space-time. So if you would count modes that are related by an SL2R transformations, you would be overcounting geometries since you're counting the same manifold multiple times.
Okay, thank you.
So Luca, sorry, now that we are here, just one question, probably stupid, but in this quantum mechanical picture, this bound state is of order one. I mean, degeneracy, right? Like there's one or two states there, or one even.
Yes, yes, yes.
On what kind of? So how is it? Is it the one that is supposed to match this e to the s0 degeneracy delta function?
Yeah, so it's just that the overall action. So the quantum mechanical theory that they write down is in principle just the quantum mechanical theory of this effective mode. And if you look how you derive it from the action, you get from the classical background on which you put the classical background around which you're expanding, you just get that the action there evaluates to e to the s0.
Oh, okay.
So the answer for the density of states that you find in that quantum mechanical system should be multiplied by e to the s0, because that just comes as, e to the s0, your partition function is e to the s0 times the path integral of this quantum mechanical Schwarzian.
Some sort of a hybrid calculation then. Because a purely
yes, they don't.
You should always get integers from a purely quantum mechanical calculation.
That's right. That's right. That's right.
Okay, thank you.
And Luca, sorry, you must go on. Oh, I'm sorry, but very quickly, I think you said it just to make sure you get these infinite number of saddles once you include that loop group part, and around each of them there is a Dusterman-Heckman type of argument protecting the answer.
That's right.
Okay,
that's right.
Nice.
And you can do you can determine the saddles as a function of chemical potentials or angular velocities for the black holes. And then you can Laplace transform the sum over saddles and their one loop determinant to get the answer for the density of states. And we will in fact see that this answer for the density of states very beautifully survives non-perturbatively. Well, I don't know if I have time. How long do I have?
Usually we are flexible with time, Luca.
Yeah, you have time, Luca. I mean, as long as you have the energy.
Okay, great.
I have a naive question. Like,
yes.
What happens to the entropy of the non-supersymmetric extremal black hole? Does it go to zero? Is that consistent with
the entropy of the non-supersymmetric extremal black hole?
Is it zero? Because the degeneracy of states goes to zero.
Yes. So as I said, we don't know whether it's zero or not. Naively, from the leading saddle, you get the answer is minus infinity, which cannot be right, which means that there's a non-perturbative correction that has to kick in at low temperatures and change that answer. I don't know whether it's zero or S0 multiplied by 0.1 I don't really have control over the calculation, unfortunately.
Okay.
The best we can start doing, you know, I hope to do this in the future, is try to take the various solutions that are known with these boundary conditions, for instance, the multi-center solutions, and see if those contribute as the temperature goes to 0 in the non-supersymmetric case. But I don't know what the answer is. It will be very, very hard to get that whether or not the answer is 1. Even in JT gravity, which is a model in which all non-perturbative corrections are known, it's actually very non-trivial to get that z of beta goes to 1 as beta goes to infinity. It's kind of an obvious thing at the level of the matrix integral, where we know that states are non-degenerate and there has to be a lowest energy state. But geometrically, it's very hard to see.
Instead of multi-filter solutions, could you also consider non-trivial manifolds replacing the singularity? I mean, because quantum gravity effects would tell you that instead of the singularity, you have non-trivial manifolds in place of the singularity. So I was wondering whether...
I don't know what the singularity means here, because I'm working in, yeah, maybe I forgot to mention this, but all these pictures and all these calculations are done in Euclidean signature. Where the interior of the black hole is, you know, not very visible. But perhaps what you're wondering is whether you could have higher genus corrections or other topologies and so on. And yes, in principle, we could have those, but we have no control over them.
Yeah.
Okay, so to summarize what I've been saying, this is the basic difference between the non-supersymmetric and supersymmetric cases. They both have modes for which the action is 0 at 0 temperature. The only difference is that the integral over the group of 0 modes turns out to give 0 in the non-supersymmetric case and 1 in the supersymmetric case, leading to drastically differing conclusions about the degeneracy of such black holes at extremality. However, even including these leading quantum corrections, there's no guarantee that we got the right answer. In fact, you know, you could take your value of S0. S0 turns out to be pi q squared, where q is an integer. In the right, yeah, where q is an integer if the electromagnetic coupling constant is related to G Newton. If you plug in q being an integer for multiple values of q, there's no way of making S0 to some power times e to the S0 to all be integer at the same time for various values of q. So can we do better? Specifically for extremal supersymmetric black holes, can we reproduce the degeneracy that one truly obtains in a microscopic model? So the basis of our comparison will be 1/8 BPS black holes in n equal 8 supergravity in 4D flat space, whose degeneracy is related to a microstate count that was done in the context of the D1, D5 system by Maldacena, Moore, and Strominger. These black holes, the count by Maldacena, Moore, and Strominger were for black holes on ADS3 times S2 times T5, but it turns out that the degeneracy or the index that they counted is related to the index of 4D black holes through something that's called the 4D 5D lift. And that's because roughly at extremality, the near horizon geometries of 4D black holes and of these 3D black holes both look the same. For 3D black holes, it's ADS2 times S1 times S2 times T5. While for black holes in 10D type 2A supergravity and 4D flat space, it looks like ADS2 times S2 times S1 times T5. So the only difference between these two black holes is the ordering of these S1 spaces. In any case, let me very briefly mention what Maldacena, Moore, and Strominger found. They found that the degeneracies of these black holes are related to the Fourier coefficients of some weak Jacobi forms of weight -2. This is the Fourier coefficient C -2 that depends on two charges of the black hole that we'll call N and L. The answer in the end is for these Fourier coefficients is found to depend only on a specific combination of N and L, which turns out to be U-duality invariant. So there is a transformation between the charges of the black hole that changes the charges of the black hole that leaves this quantity, this combination for N minus L squared invariant. So the construction that they made only considers two non-trivial charges for the black holes. But in general, in the slides that follow, we will consider a black hole in N equal A supergravity with arbitrary non-trivial charges. So here, to go from this arbitrary configuration, here Cijk is turns out to be the intersection matrix on T6. To consider this combination of charges that was considered in the string theory construction in the counting of microstates, one plugs only P1, P2, P3 to be equal to 1, Q0 to be equal to 4n, and Q1 equal to L, roughly. And one finds this value of delta. Great. So the beautiful thing about the Fourier coefficients of some weak Jacobi forms is that they admit the Hardy-Ramanujan-Rademacher expansion for the microscopic degeneracies. So this expansion is just a successively smaller exponential terms. It's 10 p.m. here, so I might my words might get a bit fumbled. So this is just the Bessel function. As you might know, the Bessel function, when delta is large, this corresponds to large charges and a large U-duality invariant. The Bessel function goes like an exponential. So this goes like e to the bi square root of delta divided by c. So when c is equal to 1, c equal 1 is the leading term in this expansion. This answer, e to the pi square root of delta, turns out to be precisely e to the area over 4g Newton for such black holes. But the beautiful thing for these Fourier coefficients of weak Jacobi forms is that this sum actually reproduces the exact integer degeneracy that is found in string theory. So in order to do that, one has to multiply this Bessel function by something that's called a Kloosterman sum. This just turns out to be a sum over exponential phases that depend on the parameter c, whose meaning we will see in a second, and on the U-duality invariant charge delta. So the question is, we have these black holes in string theory. Can we reproduce? Can we land on this Hardy-Ramanujan-Rademacher expansion exactly using the gravitational path integral? And a lot of progress has been made in this direction using localization and supergravity by these gentlemen. However, the answer was close, but the derivation wasn't really complete. The main ingredient that was missing was there were several ingredients that were missing. The main one, I would say, was the computation of the one-loop determinant around the localizing saddles and supergravity. And the second was an understanding of these zero modes that will turn out to be very similar to the zero modes that I described earlier in the talk. And the third was an understanding of how U-duality invariance comes about and why one-loop determinants turn out to be independent of the charges. U-duality invariance is something that's clear at the string theory level in the string theory constructions, but it's something that's not at all obvious at the level of the gravitational path integral for n equal 8 supergravity.
So Luca, one question.
Yes.
Would you a priori expect the gravitational path integral to produce this sum? You would want this infinite massive tower of the string modes also, right? So that would be accounted for as well.
Infinite massive tower of the string modes. I don't think in this case those contribute to the index that they look at. I think it's slightly different. You're probably imagining the result that one would get in for a black hole in ADS, right? Where in order to reproduce the partition function on the other side, you want to include all the string modes on that background. But here we're just looking at trying to reproduce the index using the gravitational path integral.
Okay.
In case, wouldn't the massive
so-
mode be exponentially damped in the expression for the index?
Sorry?
Wouldn't the massive modes be exponentially damped in the expression for the index?
Well, it turns out that we can take into account all the modes exactly. So yes, I don't think in the limit in which the temperature goes to 0, those modes will contribute. Yeah. So the setup is the following. We want to consider
representation theory, then I mean the massive modes they just don't contribute to the index, you're saying.
yes, I believe so. Yes.
Thanks.
So we start with an asymptotically ADS2 times S2 space. And since we want to match an index, why don't we actually compute an index at the level of the gravitational path integral? So in order to do that, we're going to work with by keeping beta to be a number that's very large, but finite. We'll take the limit beta go to infinity and the n. And we will actually fix the angular velocity of these black holes to be such that the Euclidean angular velocity times beta is equal to 2 pi. And if you actually trace what that means at the level of a trace in a putative dual quantum mechanical system, fixing the angular velocity to have such a value precisely corresponds to inserting -1 to the f in a trace in the putative quantum system that's dual to this path integral. And we will take at the end beta going to infinity to see if we can recover the answer obtained from string theory. And I just want to mention that this has been a recent approach that people have discussed in the world of supersymmetric black holes that is actually quite powerful. Of like fixing the temperature of the black hole and fixing the specific combination between angular velocities and temperature means that the geometries that we're studying are still supersymmetric. So usually we have the lore that the only supersymmetric black holes are the extremal ones. That turns out not to be true. If you fix this combination between the angular velocity and the temperature, it turns out that the geometry of such black holes still has killing spinors, which means that supersymmetry is still preserved. And that's precisely because this is the quantity that computes the index.
Sorry, but if we continue this to Lorentzian space, this black hole will have trouble?
Yes, because that's why I put this E. Omega, this is the Euclidean angular velocity, which corresponds to I times the Lorentzian velocity. So this is like thinking about a Lorentzian black hole that has a purely imaginary angular velocity.
Right. Okay. So it's a good Euclidean saddle point, but we shouldn't think of it.
Yeah, it's a perfectly good Euclidean saddle point. In fact, for Kerr-Newman black holes, for 4D Kerr-Newman black holes, the Euclidean, if you weak rotate Kerr-Newman black hole that has real Lorentzian angular velocity, you will get a complex Euclidean space-time. But if your Lorentzian velocity is purely imaginary, your metric is purely real. So in some sense, like these Euclidean solutions are better than the weak rotating solutions that people usually consider.
Okay.
Not better, they're just real.
Right. Thank you.
Okay, so just to understand it properly, you're trying to say that Kerr-Newman black holes are secretly supersymmetric in the limit omega e beta goes to 2 pi. Is that what you're saying?
Yes.
Okay.
Yes, and that can be checked. You can check that this geometry, even though has a smooth cigar, it doesn't have an infinite throat like the extremal black holes, has killing spinners on it. Yeah, and it actually has the beautiful property that if you compute the on-shell action on such black holes, you'll find that the on-shell action is temperature independent, which is a kind of a surprising property, but it's guaranteed by the existence of these killing spinners.
And also,
Anyway.
I suppose these Kerr-Newman black holes are extremal black holes?
Only in the limit temperature in which the temperature goes to 0.
Yeah, in the limit temperature goes to 0, they're extremal black holes.
They
right?
become extremal, yes.
Yeah, so in this way, do you expect to get a non-trivial degeneracy and a non-trivial entropy in that case for extremal black holes?
Yes.
Okay.
Yes, and we'll see what the exact answer is in this case. Okay. So then one takes these asymptotics. So we consider the asymptotically ADS2 times S2 space with that non-trivial rotation on S2. And one deforms the supergravity action in a way in which that leaves the supergravity action actually invariant of under the coupling of the deformation. So one starts by choosing out of these PSU 112 killing spinners and killing vectors that exist asymptotically. We don't know yet what's inside. We should in principle sum all geometries. But one starts by choosing a killing spinner whose squared is this combination of killing vectors. L0 here is the generator that rotates ADS2 like this. And J0 is the rotation around the z-axis of the S2 sphere. So with such killing spinner, it turns out that you could construct a deformation. This V is bilinear of fermions, where Q equivariant acts on one of the fermions. It turns out that this deformation, you can prove that the gravitational path integral is invariant under changes of lambda. Since it's invariant under changes of lambda, we might as well choose lambda going to infinity, in which case one can show that the gravitational path integral localizes to the saddles of this deformed supergravity action. More explicitly, the equations of motion associated to this deformation term, since lambda goes to infinity, we don't even care about the supergravity action when solving the equations of motion. The path integral localizes to the killing spinner acting, the supersymmetric transformation associated to the killing spinner acting on all physical fermions in the theory being equal to 0. So we can write down all these equations and see what geometries contribute. Locally, one finds that the metric is restricted, at least in a certain gauge, to be that of ADS2 times S2. However, globally, we need to still require that this killing spinner or this equation is satisfied at every point on the manifold. And there turns out to be two types of solutions that contribute. The first time a solution is a smooth ADS2 times S2 solution. This clearly has the necessary killing spinners whose square is L naught minus J naught. However, there turns out to be another type of geometry, which is an orbifold of ADS2 times S2. In principle, it shouldn't necessarily be an orbifold. It should just be ADS2 with a defect. That has the property that as I go around the defect, the amount at the same by which I rotate at the same time on S2 has to be equal to the angle of the defect. This simply comes from the fact that I want the killing spinner to exist, whose square is the generator between L0 and J0, which means that as I go around this cycle, if I square the supercharge, I need to go on the sphere by around the z-axis by the same amount.
So the full
mhm.
four-dimensional geometry is smooth, yeah, even though it looks
no. So the four-dimensional here is smooth here, but it's not smooth here. But however, if I want my full supergravity geometry in 10D to be smooth, there's ways of rotating around the various cycles of the T6 by an amount that's related to the amount that I rotate on S2, roughly. Namely, I can pick an S1 out of T6, such that if I rotate around this coordinate and this coordinate by an angle 2 pi over c, it turns out that I can obtain a smooth 5D geometry by rotating on an additional S1 by an amount that's given by 2 pi d over c, where d and c are co-prime integers. This is, if you want, generalization of the construction of Seifert manifolds, where those are 3D manifolds, where they have punctures in a two-dimensional space that for which, as you go around the punctures, you also go around an S1. Yeah.
Luca,
So
is it? Can I understand it in this way? The fact that in 4D it's singular, that the fixed point of the z action on the ADS is the origin, and on the sphere it's the pole. So that's the singularity in the 4 dimension. But if you have an additional action on S1, it's a free action.
Precisely. That's exactly the way to understand it. Yeah. Thanks.
And from the dimensional reduction point of view, this shift on the S1 will show up as a holonomy or some feature of a gauge field associated with the Kaluza-Klein.
That's exactly right. That's exactly right. And it turns out that the shift of the additional S1 is very important in reproducing the Kloosterman sum that appeared in the Rademacher expansion. So it will affect the supergravity action by an imaginary part, which will thus appear in the path integral as a phase. That phase will be the phase that appears in the Kloosterman sum. The Kloosterman sum actually has a sum over D, where one requires D and C to be co-prime.
Okay, so it's sort of in summary, you can do this calculation completely reliably in supergravity, right?
Yes.
Thank you.
So it turns out that all the smooth geometries are of this form. They're either the completely smooth one in 4D, or they're these orbifolds where this angle is quantized. It cannot be an arbitrary angle. It has to be 2 pi over c, such that there's another cycle S1 that I can do a rotation along to obtain a higher dimensional smooth manifold. And we will take the perspective that the gravitational path integral requires a sum over all these topologies. So these are not smoothly connected geometries. We will just posit that we should sum over them.
In general,
Okay.
you should have more general geometries, right? I mean,
yes, but they don't preserve the killing spinner globally.
True, but
so for instance, you can consider, like, I don't know, higher genus geometries, crazy things, and I'll actually comment on those at the end of the talk. Okay. So in addition to localizing the metric, it turns out that the path interval also this deformation also localizes the scalars in the various vector supermultiplets. These are the scalars that are usually fixed by the attractor mechanism. However, when you do localization, they're no longer fixed to their attractive value. They have an entire localization locus, which we will parametrize by phi I. So there's a continuous space of solutions. Phi I from the perspective of QV are zero modes, but from the perspective of the supergravity action, they turn out to have weight. So here I goes from 0 to the total number of vector supermultiplets in this in the n equal A theory that I'm considering, and V is related to the number of 2 cycles of T6, and it turns out to be 15. Good, and the scalar graviphoton will play a very important role in the calculation, and we'll see why in a second. So I can just take this localization locus, these solutions, all these solutions that I write down, and try to evaluate the action along the localization locus. In principle, since I'm turning on lambda to infinity, the only corrections that I have to compute to that action are just the one loop corrections around the localization locus. So for the smooth saddle, the localization locus is just parametrized by the moduli of the scalars. And the action turns out to be exactly computable on this locus and does not receive stringy corrections when you're computing an index. And it turns out to have 2 terms, a term that comes from the electromagnetic boundary term of fixing the electric charges of these black holes, and a term that comes from the n equal 8 prepotential, which turns out to be exactly computable at tree level in string theory and does not receive any higher loop corrections.
Question.
Yep.
I would suppose the localization locus just corresponds to Q naught acting on the fermion goes to 0, right? I mean, how come the scalars, I mean, what is the relationship with the scalars to that?
Well, you have some equations, right? Q naught acting on fermions can produce bosons, bosonic equations. And the bosonic equations give you equations for what phi I are. And you try to solve them. And you find that phi I is just a free parameter at the end of the day. The scalars have some profile in space in the ADS2 manifold. That's non-trivial, but some constants in these solutions are still undetermined. It turns out that 16 constants are undetermined in these solutions. And these 16 constants, these are regular numbers. They're not fields anymore. They don't depend on positions. That's why they're parameterized by these phi I's. So we have 16 of these constants that are not fixed by the localization equations that we have to integrate over.
Okay.
Okay, so this is the answer that we find on the smooth geometry. That there's some measure factor in the integral over scalars and loop vectors. And on the orbifold geometries that are now quantized, I have a similar answer. The only difference is that you can evaluate the on-shell action on the localization locus, and you find that it's suppressed by precisely 1 over c. The second feature that you find is that the one loop determinant could in principle have non-trivial C dependence. The measure could also have non-trivial C dependence. And finally, on these orbifolds, the supergravity action has non-trivial topological terms, but luckily the topological terms can actually be exactly evaluated, and they're found to be related to the Kloosterman sums. There's actually a relation between partition function of theories like Chern-Simons theory, or the 4D equivalent with a theta angle, and Kloosterman sums. In n equal weight supergravity, the prepotential turns out to be quadratic in all the scalars except the parameter corresponding to the graviphoton. That's because the scalar corresponding to the graviphoton usually appears in the denominator of the prepotential. So one thing that we can do, if the only way in which these phi 1 through phi and v appear in the action is quadratically in the prepotential, so we can just integrate them out. So if we integrate them out, we're left with the answer. If we sum over topologies, we're left with a sum over Kloosterman sums, where we now have to still do the integral over the scalar of the graviphoton times the one loop around the localizing saddle times this non-trivial function that is left after you do the integral over all the other scalars. Notice that at this point, and I'll come back to this, at this point, the partition function only seemingly depends on delta. And that's non-trivial because the action that we started with depended on QIs, and this imaginary part of the prepotential depends on the magnetic charges as well. So the fact that after we integrate out all the scalars, we're only left with a U-duality invariant is an interesting non-trivial fact. So once again, in order to compute one-loop determinants, we proceed very similarly to how we did at the beginning of the talk. Namely, the one-loop determinant piece separates into two parts. A part that comes from non-zero modes that I'll call the bulk one-loop determinant, and a part that comes from zero modes. Oh, I don't know why this depends on rho zero. This should be phi zero. Sorry for the typo. And it turns out that the contribution of the non-zero modes can be really beautifully computed using index theory. And by using the Atiyah-Bott fixed point formula, not only on ADS2 times S2, but also on these orbifolded geometries. And this is actually related to what Abhijit mentioned, which is that the orbifold geometries and ADS2 times S2 turn out to have non-trivial fixed points under the killing vectors that were equal to QEQ squared. And determining the one-loop determinant just reduces to evaluating a certain quantity at the fixed points of these killing vectors. And it turns out that for each, we work in an n equal 2 supergravity formulation, for which the off-shell formulation is known. The n equal 8 off-shell formulation is not known. We want to be off-shell since this localization locus doesn't actually put us on shell for all the fields. So it turns out that the one-loop determinant of each n equal 2 supermultiplet out of an n equal 8 theory turns out to be very complicated. However, if you multiply the results for all the supermultiplets that live in n equal 8 supergravity, the answer is remarkably simple. Namely, one finds that it's completely C independent. So each of these one-loop determinants has actually a very complicated C dependence. But overall, if you multiply all of them, the C dependence completely drops out. And the phi zero dependence is just very simple. It's just the power of phi zero. And this is actually something very similar to what happens when one does localization in n equal 4 super-Yagg mills for various quantities. If one rewrites the theory in terms of n equal 2 supermultiplets, the one-loop determinant of every n equal 2 supermultiplet is complicated. If one adds up all the supermultiplets into n equal 4, the answer turns out to be simple. But however, I don't actually know a good explanation for that a priori. I asked around and I don't think anyone does. However, we're left with determining this path integral over zero modes. And the path integral over zero modes is very similar to the one that we did before. It's also over def S14. The only difference is that now we have to evaluate the path integral over zero modes on these orbifolded geometries. And that's slightly different because the boundary conditions that large diffeomorphisms satisfy on ADS2 versus on ADS2 times S2 with a defect are also slightly different. And however, it turns out that you can do the same trick that we did before of going to slightly finite temperature and finding the partition function in the limit t goes to 0. And one finds that the answer is again simple and is given by 1 over c times phi naught. So this is the only C dependence that appears in the one loop determinant. It's from the one loop determinant of the zero mode on the orbifold background. One remarkable step that I left out but is worth mentioning is the following. Both the one loop determinant, the ultra local measure, and the determinant from integrating around phi 1 through phi and v all depended very non-trivially on the magnetic and electric charges. None of them by themselves, none of these free factors by themselves were U-duality invariant. However, if you multiply all three, the contribution of the one loop determinant, the thing from integrating out these fields, and the measure associated through phi 1 through phi and v, one finds an answer that's completely charge independent and is U-duality invariant. And I think this non-trivial cancellation is a check that our result is reliable, since nothing guaranteed that the supergravity path integral that we started with should be U-duality invariant. So putting everything together, we get the following. The integral over d phi naught is given by this power that comes from the bulk one loop determinants from the non-zero modes, this factor of 1 over c times phi naught that came from the zero modes, and this remaining part of the action evaluated on the localization locus. And it turns out that you could massage this a little bit, and this is precisely a Bessel function. The Bessel function 7/2 evaluated at an argument pi square root of delta over c. However, in order to get the exact factor of the exact c that people have found in the Rademacher expansion for the expansion of the Fourier coefficients of these weak modular forms, you actually crucially needed the factor of 1 over c that came from these zero modes evaluated on the orbifolds. But putting everything together, let's see how this formula works in practice. So let's take the example when delta is 200. So I can choose, 200 minus 1. So n is 50 and L was 1 in the formula. If you remember this, the formula was that delta is 4 n minus L squared. So 199. So this is just a U-duality invariant combination, and I just want to convince you that this formula actually converges to an integer. And I'll just show the first couple of terms. So the leading answer is given by the smooth black hole answer, which you can already see evaluating the Bessel function for such huge arguments as a huge number, but it's very far away from being an integer. The subleading saddle is like this orbifold that has a defect angle that's pi. So instead of the total angle at that around that point being 2 pi, it's now pi. And we already see that the contribution from that Bessel function times the Kloosterman phase is much smaller, just 13. And we can go on and on, adding orbifolds. And what you see is that the sum of the first 5 non-trivial saddles gives you this number, which is already very close to being an integer after only 5 saddles. So we should compare this to the exact string theory answer that can just be obtained by taking the Fourier coefficient of the weak Jacobi form, which was found to be this. So you see that we're 0.0003 off only after 5 saddles, but in principle, if I sum all the saddles, I'll recover the exact integer, and I do so very quickly. So the answer to question number 3 is that indeed the index of the black hole computed from the gravitational path integral matches the microscopic degeneracy found in string theory. So miraculously, we recover an integer from the gravitational path integral. So let me just quickly conclude.
So in this model,
yes?
you can see that there is a gap between the lowest state and the next excited state of order 1 over g Newton.
Yes. Sorry, what that wasn't important for this computation. The important fact was the degeneracy.
Right. No, I understand. This is very extremely impressive, of course. But I'm saying in particular, the stuff which was kind of universally expected as a gap, that is also present in this answer, right?
Yes. And in fact, I'll just give in this brief outlook another perspective of how this gap appears. Or maybe not another perspective, another guarantee that the gap is actually there. So let me just conclude by revisiting, since all these examples, what they have in common is that we're at the decoupling limit of these black holes. I just want to make a comparison between ADS, higher dimensional ADS holography, and ADS2 holography. So in higher dimensional holography, the scale of quantum gravity corrections is controlled by LADS over L_Planck. In ADS2 holography, there are two scales, however. There's S0, which practically is also LADS over L_Planck. In the case of black holes in flat space, this is also related to the radius of S2 measured in L_Planck units. But however, additionally, there's also the scale of the temperature over E gap. This second scale actually controls the coupling of these modes. And in particular, in the limit in which the temperature goes to 0, the black holes have a quantum mechanical effective action that's very strongly coupled. This should be contrasted to higher dimensional ADS, where if I expand fields or I try to do the gravitational path integral in the limit of 0 temperature, I'm always expanding around thermal ADS, so I only have to consider excitations of some of my light fields in the theory. And I'll get a discrete spectrum because of that. Here, the fact that I have this near 0 mode means that the density of states in ADS2 typically does not have a gap starting at extremality. So that's the major contrast with the higher dimensional ADS case. It's this presence of this other scale that controls a mode that becomes strongly coupled as the temperature is small. So the would-be 0 mode gives a non-perturbatively dense spectrum even at low energies, especially in the non-supersymmetric cases, but even at the supersymmetric cases if I go above this gap scale. Nevertheless, this is not only statistical mechanics, since we see that for extremal black holes, we can actually recover exact degeneracies. And in fact, we can see that the degeneracies were integers. However, in order to see the integrality of the spectrum, the sum over topologies is actually necessary, but is nevertheless under control. If we didn't sum over topologies, we wouldn't have gotten a valid Hilbert space description for the ground states of the system. So let's go back to this sum over topologies. Why was it under control? Well, one thing is that, as I mentioned previously, it turns out that all these other geometries that are somewhat exotic, but that people have considered lately, preserve no supercharges. So in all cases, if I consider a higher genus near horizon region, or a higher genus with multiple punctures, for each one of these punctures I can do crazy things, rotating the black hole as I go around the puncture, all of these vanish if I consider the computation of the index. And in particular, one more nice feature is that it's also connected contributions that connect multiple boundaries can also be seen to vanish in the supersymmetric case, which concretely means that even though these models are typically known to suffer from a factorization puzzle, for this specific quantities that are protected by supersymmetry do not suffer from a factorization puzzle.
I see. Sorry, Luca, just to understand that. Yes. So for this double trumpet, so to say, you're saying if you keep the Schwarzian action along with your loop action and the fermionic terms, then for the index, the double trumpet will vanish. Is that right?
Yeah, the index, it's not only the double trumpet, it's absolutely any geometry that involves trumpets.
So any
for instance, higher genus, any multi-wormhole, higher genus geometries, they all vanish.
I see. So there's a general kind of, it's some zero mode kind of proof that says
yes. You can show that one of these large super diffeomorphisms becomes a zero mode, a fermionic zero mode of the action. And fermionic zero modes of the action are nice because if you integrate over fermionic degrees of freedom that don't have weight, they give you 0.
Okay, so I have a question. Like these manifolds are essentially these higher genus ADS hyperbolic manifolds fibered over the S2, right? So, but you could have more general manifolds which are not that way, right? I mean, which are not fibered but are kind of, I mean, the S2 and the ADS, the hyperbolic manifolds, they kind of, I mean, you could have more general manifolds than just fibers. That's what I'm saying.
Yes. I agree with that. It's not a complete accounting of all 4D manifolds. In this case, it was just because the localization equations locally told us that geometry was ADS2 times S2.
Right.
That we looked at all these other possible geometries. Okay, let me mention one more thing. One could imagine changing the boundary conditions from those associated to an index to those associated to black holes that have arbitrary angular velocity, but still keep the limit t going to 0. It turns out that most of the steps that we did in our localization procedure still apply, since in the limit t going to 0, all these manifolds still have the necessary killing spinners and killing vectors to perform the localization procedure. Good. The only difference now are the boundary conditions for the super diffeomorphisms would be 0 modes that have to be treated more carefully. However, if one does the path integral over those, one finds that actually the answer for the path integral in the limit of 0 temperature is independent of the value of the Euclidean angular velocity. This implies, after a bit of thought, that the degeneracy of such black holes is the same as the index, and in particular, it implies that all such black holes are bosonic. More surprisingly, this seemingly gives us the ability to compute quantities that are not protected by supersymmetry on the boundary side, which I find very surprising. So somehow there's the gravitational path integral allows us to compute something a bit more. Yeah, yes, Shiraz, I think you have a question.
I didn't sort of understand that. I thought your whole procedure was supersymmetric localization, and now you change the boundary conditions so that localization no longer works.
Yes, so the difference is that the reason why it works is that the killing spinners and killing vectors in the limit of 0 temperature can still be defined with arbitrary boundary conditions for omega E. So it turns out that the boundary condition of omega E doesn't actually tell you, how should I say this? It just determines which cycle of your space-time is contractible. But it doesn't actually determine the fermion. It doesn't actually tell you that fermions are periodic. It tells you that fermions are periodic under the cycle in which you insert -1 to the f. But however, you can choose a different cycle around which that is contractible, around which the fermions are always anti-periodic. And that's the background on which you actually do localization.
Okay, I need to understand this. That sounds totally amazing.
Okay, so let me just say that if you do this,
Sorry,
You could also, yes,
one
yes,
more
yes,
question.
go ahead.
You sort of regulated your problem by going to finite temperature.
Yes, and taking T to 0, yes.
T to 0, and I thought you did this in this way that maintained supersymmetry previously.
Yeah, so previously we were doing an index, yes, yes, and those
so
have exact killing spinners, yes.
even in your regulated problem, right?
Yeah, even in the regulated problem.
Now
Yeah.
that presumably you cannot do unless you've got the right boundary conditions. Is that right?
Yes, yes, yes. But what we're hoping is that somehow, yeah, that this limit t goes to 0 is well defined. And, you know, at t equals 0, we know that the near horizon region has exact killing spinners, and these exact killing spinners and killing vectors that correspond to PSU 1, 1, 2. And the modes that are affected by the fact that we put the cutoff a little bit inside and no longer consider supersymmetric boundary condition, exactly supersymmetric boundary conditions, turn out to only be these near 0 modes. But for the near 0 modes, it turns out that we can do the path integral regardless of whether we put supersymmetric boundary conditions or not.
Okay. Now, as you know, Ashok had this argument about enhancement, you know, about the superalgebra, including SU2, and therefore things, only those modes that are invariant under SU2 contributing to
Yes.
index, and therefore index
So
degenerate. Is this sort of morally the same thing?
I don't think so. I think that argument relied on the existence of a putative CFT1, under which the ground states were a singlet under SU2. And I don't think that this picture in which we have an exact CFT1 on the boundary should still be necessarily trusted. I think, like, you know, this is just a description in terms of the gravitational path integral, and we explicitly see this equality between the degeneracy and the index by taking these 0 modes into account.
I see. One last and I'll stop. But is it true that all your modes are singlets under this SU2?
Yes, all the ground states turn out to be singlets.
Okay,
however, I have to say that I think these geometries, I'm not sure, maybe Ashok talked about them, I'm forgetting, but these geometries don't actually have an SU2 algebra.
The orbifolds, you mean?
The orbifolds, yeah, the SU2 is broken.
Right, right.
Only L0 and J0 are bosonic generators in that case.
Right.
So for these, it actually doesn't make sense to talk about the full SU2 algebra. In principle, the states could be charged under SU2.
Okay, sounds good. But at least for the leading saddle.
Yes.
Okay, right.
Yes, for the leading saddle, yes, you can define the asymptotic killing vectors, and yeah, like this geometry carries no charge. One thing to mention is that that's actually another, I think, non-trivial difference between higher ADS holography and this example. That in this case, you know, in higher ADS holography, only the thermal ADS contributes to the partition function, and thermal ADS corresponds to state that's a complete singlet under the conformal group. In this case, you see that there's these geometries that are not actually singlets under SL2R or SU2 that contribute to the ground state degeneracy. So you're already, in some sense, taking into account charged states, even at 0 temperature.
I see. And there is no way of grading. I'm so sorry, but is there no way of
no worries?
Yeah, is there no way of grading the full Hilbert space that you get from this with an SU2 charge? Is that
there is, yeah, you can grade everything by its angular momentum, yes.
Okay, and so in the end, when you all the states that contribute to degeneracy, are they? Yeah,
they all have J equals 0.
J equals 0. So this is, in some sense, at least morally, Ashok, this is exactly his prediction.
Yes. I just think that the logic is a little bit different, I think, because we're just not assuming the existence of a boundary theory. It's just derived from the bulk.
But I thought Ashok's argument was essentially using the near horizon geometry. And then you can call that a boundary theory if you want, but we could talk about this later, please. Yeah.
Yeah, we can talk about this later. Okay, and there's one more property, which is that as omega, even if I turn on a non-trivial angular velocity on all these geometries, they still turn out to vanish in the limit in which t goes to 0. Which means that this degeneracy, you might have thought, well, these manifolds don't contribute to the index. Maybe they contribute to the degeneracy. However, we see that that's not the case either. So what this shows is that one, not only is the index equal to the degeneracy, but also the conclusion about this gap that I mentioned earlier in the talk, where I only considered fluctuations around the ADS2 geometry. We believe it holds non-perturbatively to all orders in e to the minus s naught. So if I take any energy window starting at extremality up to something of this order, this number of states will capture the exact number of states in that energy window.
Sorry, Luca.
I want to see this.
Sorry,
yes.
It's very, very late, but can you go back to the second, just the one before this, just once, just.
Mm-hmm. Yeah,
so
yeah.
Are you saying that not just for the index, but also for degeneracy calculations, multi-boundary contributions vanish? You have a proof of that?
Yes.
But now you can't rely on some zero mode argument, right? Okay.
No. It's not a zero mode argument anymore. It's just an explicit computation from this effective action of these would-be zero modes.
Mm-hmm.
Would be you can compute the sum over saddles and the one loop determinants, and you find that the answer is 0.
I see. So
the proof is in this this paper. Well, it's not a proof, it's an argument.
So it's after the sum over all saddles, in a sense, that it vanishes.
Yes.
Is it?
Yes.
Not saddle by saddle, but is that right? Just to get it. You should go on.
Yeah, let me just make sure.
Okay, just in case.
Yeah, I think no, sorry, I'm mistaken. I think in that case you can see it vanish saddle by saddle.
Saddle by saddle.
Yes, you can see it because the one loop determinant has a behavior that goes like for each saddle in all these examples and all these free examples turns out to have a behavior that goes like beta to the 1/2.
Okay.
Times e to the something that goes like 1 over beta.
And is
and
this
then there's some
the fermionic mode is almost becoming a zero mode? Is that why this goes to 0?
Yes, that's right.
Okay.
That's right.
I see. Okay.
Yeah. Okay. So I think given that one reproduces an integer degeneracy at extremality, one can view this as a miniature example of exact ADS2 holography, where we can reproduce where the gravitational path integral can reproduce the answer that's obtained from a worldsheet dual, if you want. And I hope that there will be many more examples to come. At the end of the day, our computation only relied on n=2 supersymmetry. So the computation could be done in n=2 supergravity if one knows the prepotential exactly, or one has some control over the prepotential. And in many n=4 examples, we do have the same amount of control. So it's just a question of seeing how to adapt this localization computation in n=4 supergravity to, for instance, compute the degeneracy of black holes on R4 times K free. Sorry, R5 times K free. Okay, I will stop here. Thank you very much, and let me know if you have any questions.
Thanks a lot, Luca, for your talk.
Yeah, thanks again for the invitation.
Yeah, there were a lot of questions already, and thanks a lot for answering them so patiently. So, are
Oh
there
yeah,
any more
no problem.
questions?
Yeah, I have a question. Like,
Mm-hmm.
as you said, the Reisner-Nordstrom black hole is secretly in the supersymmetric bandwagon. I mean, it's secretly supersymmetric. So I was just wondering whether you can kind of consider the degeneracy of the states of the Reisner-Nordstrom black hole using the same sorts of arguments as you have used here.
Yes. So the statement, it's not in the same supersymmetric bandwagon, I would say. I would say that Reisner-Nordstrom does have a coincidence, as in there's this special angular velocity for which the geometry has killing spinors, and that's a fact that's unrelated to whether we're working in supergravity or in Einstein-Maxwell theory. Then there's the question about how one-loop corrections around that background look. And if I work in regular gravity and I have killing spinors, that tells me nothing about the quantum corrections around that saddle. And that's why even in the case in which I consider these black holes with the special angular velocity that seemingly corresponds to an index in just the regular gravitational system, it's not a protected quantity or nothing special happens. It's like considering trace of -1 to df e to the minus beta h in in a regular quantum mechanical system. That's not supersymmetric. You can do it. There's nothing bad with it. It just doesn't give you anything special.
Now, even in the limit t goes to 0, because in the limit t goes to 0, beta goes
even
to
in the limit. Yeah,
beta
even
goes
in the
to
limit t goes to
infinity.
0. Yeah.
So omega would go to 0. I mean, omega would, that relationship omega e beta equals pi. In that case, the omega would go to 0. And I was wondering whether that would help things in any way.
No, I think the answer, you get exactly the same answer as before. You get the partition function goes to 0 as t goes to 0. Like we can just take a non-supersymmetric UFT and compute trace of -1 to df e to the minus beta h. In the limit, even for this quantity, in the limit in which beta goes to infinity, we don't expect the answer to have any particular degeneracy. It might have sign oscillations because the state that dominates in various charge sectors might be bosonic or fermionic, but we don't expect a degeneracy.
At finite omega e beta equals 2 pi, you expect degeneracies, right? I mean, for
No.
omega and beta, where omega e and beta equals 2 pi, you expect degeneracies, right? I mean, that's when you get the killing spinor equation to be valid even for the
Yes. But the killing spinor equation, okay, it tells me something about the classical action in GR, but it doesn't tell me anything about the one-loop determinants of a theory that's not a supergravity theory.
Okay.
Sorry, Luca, it's really late and you've answered all our questions so patiently, and it's
No
brilliant.
worries, no worries.
But let me ask you something, perhaps a little vague, and maybe this is again connected to this paper by Maldacena that you talked about. But the question is this: normal ADS CFT, I mean, away from ADS2 and higher ADS, we're able to measure more than the spectrum of the theory. We're able to compute more than the spectrum of the theory. We're able to compute correlation functions and more richer observables.
Yes.
Is there some sense in which, in this ADS2 system that you're talking about, you can compute a richer class of observables? What would they be, and is there anything physically?
Yes. Well, you can compute a lot of things. So maybe I can tell you what has been computed, what we're thinking about computing, and what we're not thinking, but I would like there to be computed. Okay, so what has been computed is people have considered probe matter endpoint functions in these systems. Namely, you can insert, you can just compute what happens if in this gravitational path integral, you insert e to the minus delta L, where L is the geodesic length between 2 points on the boundary. And this result turns out to be exactly computable at any temperature. And just like the partition function, it receives very strong quantum corrections as t goes to 0. It becomes very far from the conformal answer. So the conformal answer would be that whatever the answer goes like 1 over the distance to the between the points to the power 2 delta. And that's what you get in the large temperature limit.
Sorry, and you think
and
of
for
this
large
observable,
delta?
you think of this observable as characterizing the fluctuations of the geometry? Or
Yes,
are you
yes.
also thinking of it as
Yes. It's the fluctuations of the geometry. So, for instance, you could think about the following experiment. You take a black hole that's close to extremality, and you just put a 2-point function that's well approximated by the geodesic approximation, but for which the geodesic passes through this near horizon region of the black hole. And I think those observables are very much affected by these quantum fluctuations in the near horizon region at small temperatures. Yeah, the connection between the effect on endpoint functions in just JT gravity and the exact observable that one would see, let's say for a black hole in higher DADS that's extremal, has not been fully fledged out. So that would be nice to do, to see, like, for instance, in thermal correlators, for black holes near extremality, in the backgrounds of black holes near extremality and higher DADS, how are the correlators affected? Because this would give a prediction for how thermal correlators are affected in a higher D holographic CFT. So that's one example of an observable. Another example that I think would be nice to compute is the spectrum of Hawking radiation. So here we just computed especially for black holes that decay, right? Like the non-supersymmetric black holes, we don't expect them to be stable in flat space. So we expect there to be radiation. And in the limit of low temperature, we're very far away from the semi-classical limit, and where people have speculated there's a breakdown of thermodynamics. Well, we've computed the partition function. We actually haven't computed the spectrum of Hawking radiation. And that would be very nice to compute, especially because the old arguments that tried to the old and first arguments for the weak gravity conjecture were about how these black holes, the radiation of such black holes behaves very close to extremality. So it would actually be nice to understand what the correction to the spectrum of Hawking radiation is for charged matter and for photons. At very low temperatures. You would expect there to be very large deviation from thermal spectra, since the partition function, the density of states, deviates a lot from the semi-classical answer as well. Yeah, and just another example of something that we've computed that I think is nice is one can compute the quantum corrections to the volume of an Einstein-Rosen bridge for these black holes that have low temperatures. And, for instance, you could ask whether putting it at low temperatures affects the fact that the Einstein-Rosen bridge grows linearly with time, the volume grows linearly with time. And it turns out that it doesn't. What does affect the linear growth with time is that if you take into account non-perturbative corrections like higher genus corrections and so on, you find that the volume eventually saturates. And this is what you would expect to see for any observable in an actual quantum mechanical system.
And one absolutely last question. I vaguely remember from hearing Maldasena's talk at Strings that he was talking about trying to compute matrix elements between black hole microstates, which sounded sort of, I mean, sounded like it should be not something you could access from gravity. But please, can you tell me, am I remembering right? And is there any hope of doing something
Yes,
so
you
microscopic?
are remembering right. So he was trying to compute for some observable that had a good UV description. He was trying to compute statistics of OI prime, or rather O microstate I prime. And the way in which he was doing this was he was computing, let me try to see if I remember. He was considering the maximally mixed state of BPS states. So he was considering the analog of the thermal field double state, but at zero temperature. So the thermal field double state in a sector of fixed charge is a linear combination of like, you know, BPS states. It's like BPSI, BPSI, and some over I. And then he was taking these states and inserting operators with very large Euclidean time spacings between them, which basically probed the matrix elements, this matrix element O, in you know, various inner products of some operator O that was local with the BPS states. So
So you get some statistical average over that.
You get some statistical average
Okay, that
over
sounds
that.
yeah,
Yes. He didn't have access to precisely what O BPSI prime is. In fact, I don't know how you would describe what BPSI and BPSI prime are, right? Because they don't necessarily have a geometric description.
Yeah, and even in your determinant calculation, most of the states were just in the classical part, right? It's like the one loop determinant that give you just one state.
Sorry, what do you mean? I'm not sure
I
I understand this.
When you computed your determinant, let's say in the supersymmetric case,
Mm-hmm.
for the ground state, you got one state from the actual determinant, but then it was multiplying the e to the pi s naught. The e to the pi s naught, which was not in a quantum mechanical, you know, it was just there. It was just some classical action.
Yes.
That contains the degeneracy. You see, so you can't access those states, right? I mean, the thing you can access is what you get from the determinant. Or not?
Yes, there is some hope that you can say something about something about individual states as well. I'd like to say, well, maybe let me not go into that, but for instance, you could try to ask, suppose that I start with this thermal field double state of BPS states. And then I act with these operators that, let's say I define them to be, to have some Euclidean evolution. So e to the minus tau h, e to the plus tau h, in the limit tau that goes to infinity. So these are the operators that Juan actually studies. So they're like projections of UV operators onto the BPS states. And then roughly you could start asking the following question. Suppose that I allow you to act with K on my BPSI state. And then with K squared, K cubed, so on and so forth. Is there a proof that the states that I obtain in this way at some point span the Hilbert space of my BPS states? And that's a way to hope to access, you know, in a more geometric fashion, what the space of BPS states is, because then you can just say, okay, we start with the thermal field double, whose geometric construction we know, and then we just decorate it with Ks. Of course, like eventually you'll have to decorate it with a number of Ks that's proportional to the degeneracy of the number of BPS states. So you have to act with the K to the power E to the S naught eventually.
And you'll have to see that that's where it ends, right?
And you have to see that that's where it ends, that if you add an extra state, your Hilbert space becomes overcomplete. And I would hope that this is a computation. The fact that this Hilbert space eventually has this redundancy is a computation that has the flavor that wormholes might be able to tell you that this Hilbert space eventually becomes redundant. And you know, you can consider only states up to K, something of order E to the S naught, and you'll still span your entire Hilbert space. I haven't done the computation yet. There's a similar computation that I've done for gravitational theories, in which you assume you have a QFT coupled to a gravitational theory, where that QFT has a global symmetry. There you can actually show that you can construct states, arbitrary states in gravity, without using all the charge states under the global symmetry. Anyway, I won't get into that.
Thank you so very much.
Yeah, thank you very much.
My pleasure.
It was
Extremely
totally
good.
fantastic.
Thanks.
Fantastic
Oh,
stuff.
thank you. Thank you. Thank you. I really appreciate it.
Well, one last question. I'm just curious. What is the area of a Reisner-Nordstrom black hole? Horizon area.
What is the idea?
Horizon area.
Yeah, no, I understand. Sorry, I just didn't get the
think
first part of the
quite
question. What is?
should we?
Oh,
Hello, Somnath.
you're cutting
was
off,
wondering-
Abhijit.
I was wondering if no, sorry, I was just saying that perhaps Somdatta can take this up offline, because it's quite late for you also, Luca, right? And I think people here also want to go for lunch.
Yeah, no,
is that okay,
no
Somdatta?
problem. Yes.
No, it's a simple question. I mean, whether it's zero or not, that's the question.
Whether the horizon area is zero? No, I don't think it's zero. I just think that there's black holes clearly have multiple scales, and the area is one of them. The temperature is another one. And I just think that, you know, this is an example of why the entropy of the black hole doesn't only depend on the area. Quantum corrections can also depend on the temperature.
No, but okay, in any case, I'll take it up with you later.
All right. Thank you. Thanks a
Yeah,
lot.
thank you so much again.
Thank you.
Yeah, thanks for the invitation.
Thank you very much for being so patient with all the questions. And thanks again for a wonderful talk.
Yeah, thank you.
Bye.
This has been fantastic. Yeah, thanks for the patience. Yeah, bye.